In the beginning, there was the Big Bang, a small region of space that later would become the entire visible universe. Began with light. Let there be light. But what came before the Big Bang, that primordial light? According to many cosmologists, it was inflation, the spark that ignited the hot Big Bang that we are made of, whose materials produce the hydrogen, helium, and other elements that would become stars, which would later explode and become the heavy elements that we're made of. But what caused inflation? And how did our universe begin seemingly from nothing? A single origin point to the teeming cosmos filled with light, matter, and even cosmologists that can contemplate how it all began. While inflation provides a very compelling description of the origin of the universe and how the Big Bang unfolded, you might be surprised to hear not everybody is in favor of it. A recent paper suggests that something else could have been the starting point of our universe. Two astrophysicists, including Avi Loeb from Harvard and his colleague Sonny Vigozzi from the University of Trento, wrote a letter to the Astrophysical Journal, and in it they detailed a brief history of the Big Bang inflationary theory, and where it may have gone wrong, and most importantly, how it can be tested and not proven, but falsified, for that is the job of an experimental physicist like me. All of science is built on the scientific method, the core principle of testing hypotheses with data. Anyone can propose some grand theory about how the universe or how microscopic particles work, but whether or not anyone believes it is based on two things: whether or not it explains phenomena that are or have been observed, and whether or not it could predict future phenomena. In other words, good science should be able to explain or predict, and sometimes it can do both. And there are many examples of this through the history of physics and cosmology. However, there's a disadvantage in cosmology because the timescale for evolutionary processes in the universe are unimaginably large. We really can't make future predictions because they'll be virtually untestable. So everything in cosmology operates on the scale of billions of years. We must therefore look for things that have variability. Now, it's interesting to note that there are so few things that vary in the heavens that we have names for those things. They're called planets, which come from the Greek word to wander. And even that's what a plane does. A plane is just a planet without a T. It moves. Stars, on the other hand, are basically fixed in space, as far as cosmologists' lifetimes are concerned. Stars on the verge of melting down and collapsing have probably been that way long since any cosmologist even could consider their properties. So we must focus on events where there's a wealth of data that we have and many, many events that we can see and explain. While there only is one cosmos, there are many objects within the cosmos: supernovae, stars, planets, and even entire galaxies and clusters of galaxies. So we make measurements of the present day and make models of the universe's history of how it looked in the past and try to explain how they came to be. But there's a problem in the way that we do this. It's called the lack of falsifiability. According to Karl Popper, one of the most popular of all philosophers of science, in order for something to be considered scientific, it must be falsifiable, not provable. Let's take a simple example hypothesis, like all apples are red. This premise could be proven wrong if we spotted a single green apple. All testable and effectively proven hypotheses are marked by this kind of falsifiability. It's not the only criteria. After all, astrology makes many, many predictions. Many of those are not only falsifiable, but they're falsified. I was predicted to be 6'8", blonde and blue-eyed. That didn't turn out to be true, according to my mother at least. So there's always something that, if you see it, completely disproves the hypothesis, and proving that it can't exist is how you can qualify or test the hypothesis. There's an old saying, the exception that proves the rule. It doesn't mean that it proved the rule, it means that it tests, proving in the form of testing. The problem with the Big Bang inflationary scenario, according to Dr. Vagnozzi and Dr. Loeb, is that it isn't falsifiable. You can perhaps have evidence, circumstantial evidence, for cosmic inflation, as many, many pieces of data have had, and as we've discussed with Michael Turner and other eminent cosmologists, ranging from Neil Turok to Will Kinney, we have plenty of phenomena that seem to fit and be explained by inflation, but they're not definitive proof. In other words, there are other theories that also predict these that are not consistent with inflation. So let's dig into this deeper. Where did the Big Bang come from? Well, we don't know, but as an idea, it began in the early 1900s. Around 1910, astronomer Vesto Slipher and Karl Wirtz separately measured the spectrum of distant galaxies. This tool, spectroscopy, has been discussed many times in this channel. and will continue to be. It's so powerful it allows you to measure the recessional velocity of objects in our galaxy or in distant galaxies away from the Milky Way. A few years after Slipher and Wirtz's discoveries that almost all galaxies are extragalactic nebula or nebulae, or spiral nebulae as they were called back then, it seemed as if all of them were moving away or having a redshift, a recessional velocity. That was strange, because other nebulae like the Orion Nebula had components that were moving towards and away the Earth. In the same decade, in 1915, Einstein's work on general relativity seemed to suggest that the universe can't be static. It either could be expanding or converging, but there was no way that it could be stationary unless, as Einstein did, he inserted the so-called cosmological term of vacuum energy density that balanced the collapsing nature of the ordinary matter in the universe and counteracted it. He later called that his biggest blunder, and I like to think about what his career could have been like if he didn't make that blunder. Imagine it. So, later on, Edwin Hubble came up with observations that established Hubble's law, based on Celia Leavitt's predictions of the discoveries of the relationship between the period and the luminosity of so-called Cepheid variables. Now we know that as Leavitt's law. So Hubble, with a combination of distance measurements from Leavitt and redshift measurements from Slipher et al., had a prediction that every galaxy was actually redshifting. The farther away it was, the faster it was receding. What Hubble showed was that the universe was not static. It was not even collapsing. It was expanding. So what Einstein had suggested to obtain a static universe was shown to be impossible. The universe was changing. It was dynamic. It definitely wasn't static. Putting them both together, it was clear that the universe had been expanding for a long time. Going backwards in time, if you think about it as a movie reeled backwards in time, you'll steadily get to a denser and denser universe. Everything got closer together as you went back in time. And this agreed with the ideas of Lemaitre, who's a Belgian Catholic priest, who had come up with the model before Hubble's connection between redshift and distance. Lemaitre did that back in 1927. He described the origin of the universe as a so-called primeval atom, a nucleus that exploded somehow into an expanding configuration, where all the matter in the universe was combined to a giant atom, effectively. He predicted that eventually this expansion would result in the expansion of the matter particles that had come together as galaxies, and they would all be moving away, except for a handful that are gravitationally bound to the Milky Way, or we're bound to it, in the case of the Andromeda Galaxy or the satellite galaxies, the Magellanic Clouds that orbit around the Milky Way. Those are the only exceptions. Only a handful, 10 or 20 galaxies, are coming towards us or static with respect to the Milky Way, and 100 billion other galaxies are moving away from us. The second pillar of the Big Bang's narrative is the cosmic microwave background. The leftover heat after the fusion of the first elements in the periodic table is the light source that we call the cosmic microwave background, or CMB. These are the relic photons, the leftover heat. These are particles, the earliest particles of light, the earliest, oldest photons. They trace themselves to the hot, dense phase in the first few minutes of the Big Bang, and as the universe cooled off from the first few minutes out to 380,000 years when the first atoms formed, so the duration from the first nuclei to form in the first 3 minutes of the universe's history, to the CMB production when the first atoms formed, was 380,000 years. Inflation explains the energy necessary to create the first nuclei, which would later become the first atoms, and it does so by suffusing the universe with heat and light, which is the result of the dynamics of a so-called scalar field evolving under what's called slow roll from a higher energy state to a lower energy state, a true vacuum state. And that releases energy, as it does in phase transitions and those heating packs that you use when you're skiing, or in a phase transition of sodium acetate, like I did in a demonstration at the Royal Institution recently. There are many people who suggested along the history of inflation that inflation is not correct. The three most fierce critics of the inflationary paradigm have been guests on this podcast: Paul Steinhardt, Neil Turok, and Sir Roger Penrose, winner of the 2020 Nobel Prize. But inflation makes other predictions as well, including the absence of observation of magnetic monopoles, which is also true, but there are many things that can prevent magnetic monopoles from being observed, including they might not exist. Past guest on the Into the Impossible podcast, Lord Martin Rees, a British cosmologist, summarized it thusly: skeptics about exotic physics may not be hugely impressed by a theoretical argument to explain the absence of particles that are themselves hypothetical. Preventative measurement can readily seem 100% effective against a disease that doesn't exist. So getting back to Vagnozzi and Loeb's Astrophysical Journal letter, They intend to solve the problem of the specific testability or falsifiability of specific models of inflation. They suggest that any general model of inflation will probably be falsifiable, but the whole inflationary paradigm, in their words, is not falsifiable. So, to make it easier to study and characterize different models of inflation and the entire program of inflationary falsification, they proposed a model-independent criteria that would discriminate between inflation and other ideas of the early universe's formation. So what's the big idea? Well, inflation explains the absence of magnetic monopoles by positing the hyper-superluminal expansion of space-time, such that even if there were a huge density of them in the early moments of the universe's history, by the time inflation is over, there might only be one in our entire observable universe. So they get spread out too far to detect them. Well, Vagnozzi and Loeb proposed that something similar would happen, not necessarily with magnetic monopoles, but another harbinger of inflation, gravitons. Primordial gravitational waves. Now, gravitons have never been detected. They're the particle analog of gravitational waves, in the same way that photons are the quantum mechanical particle instantiation of electromagnetic waves. According to Loeb and Vagnozzi, the two researchers proposed that in the early universe, primordial gravitons would be diffused away, forming a cosmic gravitational background. If inflation as an abstract concept were accurate, this cosmic gravitational wave background, or CGB, would have been spread out to being undetectable. Therefore, they argue if you were to measure a cosmic graviton background, it would prove the whole inflationary paradigm wrong, because these should not be possible to observe in the same way that inflation predicts we should not be able to observe magnetic monopoles. Observing gravitational waves in their quantum form would prove the inflationary paradigm wrong, or therefore it would falsify it. Now, the CGB sounds familiar. It's in resonance with the CMB, the cosmic microwave background. Whereas the cosmic microwave background are electromagnetic waves. They're no longer photons, really, although, of course, at a quantum level they are. The cosmic gravitational wave background, or graviton background, is leftover ripples in space-time at the quantum level, stretched out to cosmic scales via the expansion of the universe. Now, we're searching for that with many experiments, and we claimed a detection of that in 2014, as we talked about many, many times, and it is the subject of my book, Losing the Nobel Prize, available wherever books are sold, and click on the link below to get whisked away. We did claim we detected B-mode polarization, which would be indicative of the CGB, the cosmic gravitational wave background. However, in 2015, we essentially retracted our conclusion, saying that the signal was primarily caused by dust. We did so in collaboration with the Planck experiment, which had the data on dust that BICEP 2 lacked. Even looking at the CMB like we've been doing, our technology hasn't reached the point of confirming things one way or another, so we're a little ways out from being able to detect the cosmic gravitational wave background and prove this once and for all. Proving a paradigm wrong is helpful in letting you observe what is possible to detect. So if Vagnozzi and Loeb are looking for a way to make it falsifiable, they must also be proposing an alternative. That's the bouncing cosmological model. Bouncing cosmological models are not new. They've been around for a long time. We've talked about it with Anna Aegis and others on this very podcast. So before the Big Bang, they posit that a universe came together and bounced back, and that bounce produced the heat and energy, but it did not require a fundamental quantum mechanical period. It could have been a classical bounce, leaving behind no cosmic gravitons, and so that would allow falsifiability of the inflationary model if that model were correct. There are also other cosmologies like string gas cosmology, who we've talked about with my old professor Robert Brandenberger here. And so the key message is that the CMB and its polarization, the very thing that I've dedicated my experimental career to, is not used to prove models of cosmology. We cannot prove inflation or prove the bouncing cosmology right or wrong. All we can do is falsify other alternatives. So by observing the cosmic microwave background's B-mode polarization, if it has the right properties, in one hand, could falsify or reject models more easily than it can actually prove models. And if you want to know more about these alternative models, click here for a playlist that I've cultivated just for you. And don't forget to hit the like button if you want to see more content like this.